Hello everyone and welcome to our online presentation of multi-objective optimization of robotically bent in-situ reinforcement system. I am Milad Showkatbakhsh and I'm here with you with Elif Erdine and Alvaro Lopez Rodriguez.
The research presented in this paper is part of an international workshop, Architectural Association Istanbul Visiting School. This is a 2-week workshop that takes place annually. The workshop is structured in 2 stages. During the first stage, participants familiarize themselves with relevant material processes, computational methods, and fabrication techniques. They are organized into teams and propose an architectural intervention based on the research agenda. Then a competition is held, and the winning proposal is fully fabricated and assembled as a full-scale prototype in the second stage of the workshop. The primary contribution of the research is a demonstration of a multi-objective optimization methodology that incorporates various fitness objectives related to form finding, materiality, fabrication, as well as finite element analysis during the early stages of design. This has been an ongoing research for the past 2 years. Our research topic has been the development of formwork generation and concrete application for complex geometries. Particularly, our key consideration has been the reduction of formwork waste material. In this first iteration, a computational workflow for producing only positive elements from EPS as stay-in-place formwork was realized. This process was governed by the geometrical rules of robotic cut wire cutting. The stay-in-place formwork was later covered with GRC technology.
The second iteration of this ongoing research was to produce complex double curved surfaces to be fabricated with the application of mesh reinforcement concrete. The design process started by producing ideas by the group works, as Elif mentioned. Collectively, the design proposal was selected and created. In order to benefit from multi-objective optimization processes, we needed to parameterize the design proposal to create a design problem onto which the generative design process will be operating. The intention of this stage was to calibrate and fine-tune the proposed design idea in order to be fabricated. In general, evolutionary computation has been applied in many different disciplines that have struggled to solve complex problems through traditional means and have resorted to evolutionary process for inspiration. Whether it was in design, music, economics, sociology, the evolutionary process has served as a robust mechanism to help address complex problems. The reparameterization process is a necessary stage in order to apply the evolutionary computation at all stages of the design process, whether it is in early phases of or the late stages of the design, which in this paper we explored their application at the late stage of the design development by fine-tuning a proposed design idea that was achieved by a group work. The first step was to parameterize the design proposal in order to create the design problem. The second was to define the constraints and objectives which are the backbone of the evolutionary computation process. The objectives were to optimize the structural performance by reducing the structural displacement value of the shell. By changing the form through control points of the geometry, it allows the generative process to generate variable and viable solutions. The second objective was to create pockets of flat surfaces on the geometry. This was introduced to ensure the practicality of the phenotype or geometry, as it was stated in the design brief that the output was going to function as a piece of urban furniture. And at last, the third objective was to use metal rods as less as possible in the fabrication system. It is worth mentioning that the relationship between the genes introduced to the process and the objectives also, and the algorithmic way of setting up the design problem, was to ensure the angles that rods are creating are within a defined domain. This is, however, out of the context and the scope of this paper and will be thoroughly explained in the context of another publication. After creating the design problem, we used genetic algorithm through the plugin called Wallasey in Grasshopper in order to address the defined set of objectives. The application of evolutionary computation through genetic algorithm in order to solve complex problems has been around since mid-20th century, and in recent years it has gained some ground in architecture and design discipline due to the availability of the application, which allowed to incorporate this iterative process over and over. For this paper, we used visual programming platform of Rhino called Grasshopper and the evolution solver called Wallasey. The generating And the generation process and the iteration, as it is pictured in the purple circles, include creating random population, evaluation, selection, and according to the set of evaluation criteria, reporting the final population set. The setting that were used for the evolutionary solver is as follows. The further explanation of each title is available at the source material. However, the population size was concluded from a set of test runs in order to make sure that simulation will produce the most optimized results it can. As you can see from the parallel coordinate plot, that all three objectives were optimized accordingly, and plotting all of the graphs of three objectives side by side, we can understand that generative design process produce solutions with optimized values. The explanation of the graphs and the way that it can be read, it is available at the source material. The third step of this process was to analyze the generated population and select the individuals suitable for the fabrication. Since Wolsey stores the evolutionary history of the simulation, it was easy to access the population and filter down the population to a smaller set of Pareto and highest ranked individuals for each objectives. Studying the population alongside with the data associated with each individual was a much more efficient way of selecting the final individual to be fabricated. On the left, we see the selected solution that was chosen according to a set of selection criteria that is explained thoroughly in the paper. The generative design process and the significance of understanding the data within this process is extremely important. Since the formal similarity of the generative solutions will make the selection process impossible, accompanying the data to the geometry also ensures that the selected solution checks objective performance required for the fabrication. After selecting the geometry to fabricate, the optimized geometry were developed further to prepare it for fabrication process, which is divided into steps of robotic rod bending, creating frames, application of the mesh on the top of the skeleton, and spraying the concrete at the end. So the entire workflow of the design process from the initial form finding to the optimization looks something like this. Now I will hand over to the presentation to Alvaro to explain the overall robotic fabrication part, which is worth mentioning that it will be thoroughly investigated in the context of different publication as well.
Very much. So for the robot bending process, we set up a fixing surface where we place a series of guidance and fixing elements that were bespoke for the process. The robot was programmed also with robots plugin for Grasshopper, and to ensure or to avoid the collisions with the robot during the bending process, we applied a series of security areas around the robot during the fabrication process. So all the jigs were bespoke for this specific robot bending system, and they were all 3D printed since they were quite experimental. We used jigs for both fixing and guiding the rods into the fixing surface. And also, as you can see here, we use a vise to ensure that the rods were completely fixed during the bending process. For the bending tool, we use a CNC-made out-of-steel piece that contains a series of rods to smooth a soft and continuous bending process. As you can see, we also implemented a series of extra bending angles to avoid the backlash of the rod after the bending process with the robot. As a result, we got a series of robot bend elements that were cataloged and categorized for the assembly process. This assembly process was made out of a series of wood frames where we were locating all the bend rods in a specific position due to the marking. So they were ready to be applied all mesh for the concrete spraying process.
After the rods were bent, a textile stay-in-place formwork was installed and secured over the rods. The GRC machine was then brought on the construction site. Here the concrete mixture is prepared. Long fiber threads are cut into pieces and mixed with the concrete, and this is followed by the application of the concrete mixture via spraying. The method of application takes place as 3 layers of concrete mixture. The first 2 layers, each 3 to 4 millimeters thick, contain fiber threads. The final layer, which is 2 to 3 millimeters thick, does not contain any fibers for a smooth finish. This process is followed by the analog rolling to compress the deposited material. The curing time for the overall prototype has taken 24 to 48 hours. And it is also important to mention that the mixture was adjusted to minimize its thickness to reduce weight. It is also important here to mention that Fibrobeton has been our industry partner for the past 2 years, and they have been a very significant factor of the research process. In conclusion, the proposed method utilizes an iterative process of generating a population of candidates, allowing for a wider morphological variation. What is key here is the coupling of geometry and data during analysis and evaluation stages. This multi-objective optimization method, as demonstrated in this paper, can be employed in various stages of design. It can also be further extended across various scales to save energy, material, and cost in architectural projects. This method can become a robust and powerful alternative to a single preference-based approach.
And at the end, I would like to thank you all of our 2019 staff, assistants, tutors, and students for their efforts and dedication in the workshop, as everyone played a vital role in the process and the success of the project. I would like to thank our sponsor Fibrobeton once again with their unconditional support and help at all stages of the design to fabrication. And at the end, thank you for listening to our presentation, and we hope you enjoy the publication. We are very much looking forward to our conversation in the online conference. Be safe and goodbye.